So we are going to look at weighted graphs. So the edges are now going to have weights on them. So a complete graph whose edges have numbers attached to them is called a weighted graph, and actually doesn't have to be complete graph to be a weighted graph. You could have other weighted graphs. The numbers shown along the edges are called weights. So AB has weight 10, the edge CD has weight 12. When we model real-world problems, the edges will be labeled with weights which represent, for example, cost, distance, or time, because we are going to want to minimize the time, minimize the distance, minimize the cost of a circuit. Okay, so we will see later on that those will actually maybe be dollars, for example. The graph is a model for one-way airfares for cities A, B, and C, and D. Use the weighted graph to find the cost of the trip for the Hamilton circuit A, B, D, C, A. So we want to find the total cost. Again, these are dollars. So if I fly from A to B, that's going to cost me $100. Again, we're following this circuit here. A, B. If you want to trace it ahead of time, you can. A, B, D, C, A is the Hamilton circuit. Again, visiting each city exactly one time. All right, so we first go 190, and then we went down here to 155. We're going to add these together because we want the total cost. Right, each of these is airfare. That's $179 to fly from D to C, and back here to A is $124. And if you add those up, 190 plus 155 plus 179 plus 124, that should give you $648 to make that trip. So again, I mentioned this, finding the minimal cost Hamilton circuit. Again, there's many different Hamilton circuits, but if we want to visit each city exactly once, we want to find the least cost trip. And this is called the traveling salesman problem. All right? Such a circuit, to find like if you look at this picture, this traveling salesman wants to visit towns B, C, D, and E and end up in A, and there's many different ways of doing that, but we want to look at finding the optimal Hamilton circuit or the optimal solution. You might hear that as well. So we have different methods to find the optimal circuit. The first one is the brute force method, and you can tell by its name that usually brute force is going to mean very time consuming. This is the only method that guarantees the optimal solution. However, with a large set of vertices, this can be very time consuming even with the computer, because the brute force method, you're going to have to list all the Hamilton circuits, add up the weights for each one, and then find the cheapest total weight. And we're going to do an example of this on a smaller set of vertices. But there is a slide that sort of tells you how time consuming this is, and we can talk about that a little bit more later. We also have the nearest neighbor algorithm, and it's a good method to find the optimal solution, but it's approximation. It could give you the optimal solution, but it may not, but it will give you a good solution. And then we also have the best edge method. It's also called the cheapest link algorithm. And again, it does not guarantee an optimal solution, although it should give you a good approximate optimal solution. So the brute force method, you model the problem, the application problem, with a weighted graph. You make a list of all the possible Hamilton circuits. Recall that there are n-1 factorial possible circuits. However, you can cross out the circuits that read the same forward and backward, because if you add up the weights around forward and backward, the total weights will be the same. Determine the sum of the weights of the edges for each of these Hamilton circuits. Again, we're going to find the total cost circuit. And then the Hamilton circuit with a minimum sum, right, the cheapest cost is the optimal solution. That is the brute force method. So let's see how this works. Find the minimum cost circuit using the brute force method, and we will start at city A just for because it tells us to. Then the final answer will actually be written one of two ways, and I'll talk about that in a second. So again, we're going to list all possible circuits, and again, it's that same four vertices. So we want to do 4 minus 1 or 3 factorial, right? Which is 3 times 2 times 1 is 6 circuits. So we're going to have to list out 6, starting with A. And we already actually did this, right? Remember, we fix A and fix the first two, A, B, C, D, back to A, B, D, C, back to A. Then we do the ones that start with AC, AC, BD, oops, BD, AC, DB, and of course they end with A. And then the ones that start with D, AD, BC, AD, CB, and then end with A. You might also hear circuits. You might see also that they are called cycles. So it might be Hamilton circuits, Hamilton cycles, Hamiltonian circuits, Hamiltonian cycles. Circuits and cycles mean the same thing. All right, so let's go ahead and for the brute force method, we find out how many possible circuits there are, which we just decided there's 6. We have to find the weight of each circuit and then find the one with the minimal weight. So as you can see, this can be very time consuming. And here we only have 4 vertices. So the first one's A, B, C, D, A. So that's 190 plus 126 plus 179 plus 157. Probably good if you use a pencil in your lecture notes, because then you can erase it after you've found the cost. 179 plus 157. For that one, I get 652. ABDCA, so AB, and this time we go ABD, which is 155, to C, which is 179, back to A, which is 124. So that should give you 648. So that one's a little cheaper. So that one looks better than the first one we had. AC 124, B 126, D 155, A 157. $562, so that one's even better than the first two in terms of cost. Now, as I mentioned, some of them will be the same circuit but going backwards. If you look at this first circuit, ABCDA, and you read it backwards, it's AC, AD, CBA, AD, CBA. If you read it backwards, right, AD, CBA, AD, CBA, it's this one. So if you go around if you go around A, B, C, D, A, or you go around backwards, A, D, C, B, A, the cost is obviously going to be the same. You're going the same, hitting the same edges. So this should actually be the same as the top one. All right. And let's look at the second one. I mean, you can certainly write them all up and add them up. I'm just trying to save you a little bit of time. The first one, AB, or the second one, ABDCA, if you read it backwards, it's ACDBA, ACDBA. So these two are then the same. All right, so this one should also be 648. And then if we look at this one, ACBDA, and you read it backwards, ADBCA, it's the same as this one. So the total will be 562. Okay. So you will see that you can get the same forward and backwards. So there will always be you know, half of them that are duplicates of the other one. So the way that, and that's why you can see, note, the final answer can be written as one of two ways. So these are the lowest. And if you don't quite understand that backwards thing, you can just compute them all out like we did the first three. Those are the lowest. So our answer can be written either way, ACBDA or ADBCA. Right? Either one of these two are the lowest, and it doesn't matter which way you write it. So here we talk about the brute force drawback. It is very time consuming. If we have 25 cities, then there will be 24 factorial. If you put that in your calculator, it will actually put it in scientific notation, because 24 times 23 times 22 is so big. It's 6 times 10 to the 23rd, right? Which is then 23 zeros, right? That's a large number. So the brute force algorithm will give an optimal tour. However, it is time consuming. Even with the computer, if Hamiltonian circuits are generated at the rate of 1 million a second, it would take 10 billion years to generate them all on this 25 cities.